Hi everybody. So last time we talked about two very important phenomena related to wave optics. These two are interference and diffractions. So we have done a detail about interference and diffractions. So today I'm going to start with the comparing, right? The difference between diffraction and interference. Okay, so I've done 4 points. Okay, so let me start something like this. When we talk about interference, we talk about light has to come from two states, and the light from two states interfere each other, or superimposition of light coming from two source or two coherent source give rise what we call as interference. Okay, so unlike interference, in case of diffractions, it is a superposition of a wave coming from the same slit. Alright, so that means a particular slit is act as a source, and these particular slits is divided into so many small parts, and each individual part act as a source. So therefore we are taking a light from entire parts of a slit. So entire parts of a slit act as a source, and a light from an entire part or all the parts of a slit and give rise the light from all the parts of slits superimpose each other and give you what we call as this is the difference, right? So you have so many sources. Here we talk about only two sources. Here we talk about so many sources. So that's the one big difference. And then as far as the second difference are concerned, in case of interference, the central brights and all other brights are of equally brightness. The intensity of a central bright and the other bright or constructed interference are equally bright. The brightness are equal, and the brightness is I is equal to 4 times the brightness of a light from each slit. However, in case of a diffractions, the center would be a brightest. The central bright is going to be a brightest, that is 4 times the brightness of individual light. And what about the secondary brightness, right? Intensity of secondary brightness, that is the first, secondary, third, second, third, fourth, etc. has a brightness 1/3, 1/5 and 1/7 of its center. That means the brightness decreases as you go away from center bright. So this is the second difference. The third difference is regarding the angular position of an bright and a dark. So in case of angular position of bright, in case of interference, is what is given as this. This is the angular. I'm sorry, right? Third part is something like this. Angular position is a fourth point. The third point is that in case of interference, the width of a fringe, either it is a dark or a bright of equally spaced, then the width of individual brightness or bright band or a dark band is given by lambda d by small d, whereas in case of diffractions, it is of not equally spaced. Interference, it is of equally spaced. However, in case of a diffractions, center is going to be twice of its secondary maxima. So that means the width of a central bright is twice as wide as the other secondary maximum. So this is the third difference. The last difference is what we talk about angular position, which I told you now. The angular position, the secondary maxima or the angular position is given by n lambda by d, and the dark fringe position is n plus 1/2 lambda by d, whereas in case of diffractions, secondary maximas are given by this. So this is just the opposite. Alright. This is just opposite. And the secondary minimas are given by this. So these are the differences between diffraction and interference. So this is very important for examination. Examination point of view, it is very important. So purposely I have written the differences between diffraction and interference. So this is very important for exam. All right. So now next what I'm going to do is, this is the topic which I'm going to do today, the resolving power of optical instrument. So this is what we have today. So we are going to discuss the resolving power of two optical instruments, that is a microscope and telescope. When I did ray optics, we talk about magnification of telescope, magnification of microscope. When we talk about telescope in ray optics, I told you that we discuss two very important aspects in a telescope and a microscope. These two concepts or aspects are, one is magnifications, another one is resolving powers. So I told you that resolving power comes under wave optics. So this is what we are going to do today, right? So when I talk about resolving power, or the term itself, resolution or resolving power, yeah, you might have come across this kind of concept in your day-to-day lives. So when I talk about resolving power is simply defined like a simple, in a simple definition, it is defined as ability of an optical instrument to distinguish, all right, to distinguish two objects, all right, that means images, right? If we could able to distinguish two images, then we say that we resolve two images, and if we could not distinguish, that means image of one object overlap with an image of another object, so therefore we could not distinguish two images, then we say that we could not resolve. So that is what we call. So right. So this we may come across, right? And then this effect is all because of wave nature of light. All right. This is what we call a wave nature of light. So resolving power itself is a limit. All right. Resolving power is a limit. A limit to that particular optical instrument, and that limit is because of wave nature of light. Alright, this limit is all because of wave nature. So I say, so these two points are, we can distinguish these 2 points. That means these 2 points are distinguishable, they are resolved. Alright, so now if I do like this, these two circles are not exactly resolved, but you could able to distinguish, right? So now if I say it is something like this, is one overlap with another, that we cannot distinguish two circles, so therefore it is not resolved. Alright, so this is what we have. So now look at here, we shall start with an example, right? You might have heard about something called a binary stars, right? When we use our naked eye and see our stars, and we could not distinguish two stars. Alright, the example I would like to give you is these are the point, right? So this is the star. This actually we have a two star, but when we use our naked eye, when we see without telescopes, we could not distinguish two stars. These are the images of two stars. Images of two stars are overlap each other. Why? Because this goes beyond our resolving power. This goes beyond our resolution of our eye, naked eye, right? So therefore we could not distinguish two stars. Alright, we could see only one star. Now when we use a telescope having resolving power greater than naked eye, so we could see two stars. Now we could see two stars. Alright, these two are very close to each other. We could see two stars. Now if we use a better telescope, alright, then we could see two separate stars. Alright, actually stars are same. All the three pictures are the pictures of the same star. Alright, the difference is that when we use the naked eye, we use telescope, and we use a telescope with a better resolving power. So that is all because of resolving power. Alright, so this is so therefore if we use a better telescope, we could see to separate stars. So this is what we have. So what we have is in case of telescope. Alright, so let's start with the telescope. So this is an example, this is a ray diagram of telescope. So telescope consists of the objective lens and eyepiece. So look at here. When we talk about resolving power, it is all objective lens that determines resolving powers. It is all that objective lens that determine resolving powers. So if this objective lens could not resolve, let's say two stars, could not resolve two images, then the further, right, this lens will not further resolve. Maybe this lens could magnify the images, however this lens could not resolve. So therefore what I would like to convey you is, so resolving power is all determined by objective lens. Resolving power is all determined by objective lens. So therefore we have learned that we require a huge apertures or the huge objective lens in order to get better resolving power. So this is what we are going to discuss today now. Alright. So this is what we have. Now let's say if light is of a ray nature, then we won't come across a phenomenon called resolving power. Alright, so this is the example. In case of ray optics, the light from a source, when the light from a source pass through this lens, we will get a point. This is the point image. We will get a point image. We would get point image. If we get a point image, then we will say that the resolving power, the limit of the resolving power is going there won't be any limit. Alright, there won't be any limit as far as the resolving power is concerned. Therefore, resolving power would be infinity if light is ray in nature. However, in actual case, light is no way ray in nature, right? Since the light is not not in a ray nature, so therefore what we have, since the light is wave nature, diffraction take place. Alright, so this is what we have. This is diffractions. So because of a light having a wave nature, instead of a point image, which we found in case of ray optics, we get a bright spot. This is a bright spot, alright, spot with a finite size. With the finite size. So the bigger the size, the bright size is, the resolving power is smaller. If we could get a smaller bright spot for a given astronomical objects, then better would be resolving power. So now this is wave optics. This is what we call as a wave optics. Because of a wave optics, we get finite bright spot. Alright, because of this finite bright spot, we have something called resolving power. Alright, so this is what we have. And now we would like to have we would like to have objective lens. So now let's say I have a parallel incident waves. Let's say a plane incident wave. Let's say wave fall on this. This is the objective lens having a size 2a. Now we will say that since it undergo a diffraction, we get a diffraction patterns, and this is going to be a diffraction patterns. So diffraction pattern is such that we get a center bright spots, and then we would get after that central bright spot we get concentrics, dark bright. This is what we have. So this is the waveforms. This is the wave. This is the central bright, and this is the secondary bright. This is what we get, and this is the diffraction patterns. This is the diffraction patterns when a light passes through an objective lens. And we know that the radius, right? Look at here, the radius of this is given by, the radius of this bright spot is given by 0.61 lambda divided by f, right? This is the radius of diffraction pattern. This is the radius of diffraction patterns. This is the radius of diffraction pattern. And I told you that bigger the radius is, the resolving power is smaller, right? Now we would like to, what we would like to do is that, now since object is very far, whenever we talk about the telescope, object is very far, therefore I have considered plane incident wave. Alright, why I consider a plane incident wave? Object is at infinity. If object is at infinity, then image is going to be at a focal plane, right? Image at focal planes. Image at a focal plane, and this is going to be our focal plane, and this is going to be our image distance. This is going to be our image distance, which is going to be f. Which is going to be f, right? So now look at here. Now we can write is that f theta naught. Let's say let me put delta theta. F delta theta is going to be r. All right, f delta theta is going to be r, which is going to be 0.61 lambda f by a. So therefore, f delta theta is what we write as ff, cancel out, and this delta theta is what we call as angular separations. This is what we call as angular separations. Angular separations. This is what we call as angular separation of bright spot. Angular separation of a bright spot. And as I told you that if this bright spot is bigger, then resolving power is less. If this bright spot is smaller, then angular separation would be smaller, and then the resolving power is going to be less. Resolving power is going to be greater. Alright. So therefore we would like to define what we call as a resolving power. We say resolving power is a reciprocal of angular separations. This is what we have. Resolving power is what we define as reciprocal of angular separations, which is defined as the A divided by 0.61 lambda. So this is the resolving power. Now what is resolving power? I'm going to write here resolving power is equal to A divided by 0.61 lambda. This is what we have, resolving power. Now this is the resolving power. Now let's see, right? So this expression indicates that a resolving power is directly proportional to size of an objective lens. So therefore, when we discuss ray optics, we say that we prefer a bigger objective lens for two main purpose. That is getting a better light gathering power, and then second one is better resolving power. So this tells that resolving power is directly proportional to size of an objective lens. This is one, right? This is one. So therefore, we always try to construct as big as possible, right? So objective lens should be as big as possible. So therefore, we talk about how to build bigger objective lens that we have discussed detail in ray optics. Now another part is that resolving power again is inversely proportional to the wavelengths. So as far as optical telescopes are concerned, we have to use this lambda. Lambda is going to be from 700 nanometer to 400 nanometer. This is for optical telescope. So this day we built what we call X-ray telescope. So when we use, what is the advantage of using X-ray telescope is that when you talk about X-ray, then lambda is going to become a much smaller than a visible light. So if lambda goes very small, then resolving power is going to increase manifold, right? So therefore, X-ray telescopes are these days we find X-ray telescopes and which could see stars having a distance of thousands of light years. So this is what we have. So this is not an optical telescope. We use X-ray, and then and we could see much further distance. So this is what we have, right? And then again what we so normally speaking, when we talk about resolving power, all right, we divide this into a three part. Just resolve, and then unresolved and completely resolved. So this is what we have. This is the fully resolved. So that means we took two important distance. One is the size. One is what we call as a radius, right? Radius of bright spot. Smaller the radius, the better is the resolving power. And another one is the distance. Distance between two images. Let's say it is divided by D, this is divided by R. So now look at here. For just resolved, if a distance, this is a distance, right? Distance between the two center of images, right? If a distance is equal to a radius, alright, if a distance is equal to a radius, then we call it as a just resolve. It comes something like this. Alright, this is better diagram here. Or unresolved is if a distance is smaller than radius, then this is what we call as unresolved. Alright, this is unresolved. Distance could be this, and a radius could be this. So distance is smaller than a radius. So fully resolved means if a distance is much greater than r, so this is what we have. This is fully resolved. This distance is this is r. So this is how we define, right? This is what we call as a Rayleigh criterion in case of resolution. That this is not there in our syllabus, just for your information I'm giving you, right? And then the same I can define in terms of central bright. Look at here. Again, this is unresolved. Two bright spots overlap each other. Alright, this wave represents a bright spot, and in this case, this is just resolved. Just resolved is one peak, right? Peak of one bright spot or central bright coincide with the next dark or dark positions. So this is what we have. This is what we call a just resolve, and this is completely resolved. This is completely resolved. All right. So this is what we have in terms of in case of we represent this in terms of wave, right? A diffraction pattern, right? So this is what we have, and this is all about diffraction, or this is all about resolving power of telescope. Now I would like to start resolving power of microscope. This is microscope. So this is I have again like in the previous we have done a telescope. This is the factor is objective length. Objective length is the one that determines resolving powers. That resolve to a near object. Look at here. Now you may come across. when diffraction is significant. So look at here, if when I talk about microscopes, very two tiny objects, if I say if a distance between two tiny objects, let's say I just take these two tiny objects. If a distance between these two tiny objects, is, let's say, d, if a d is comparable to, if this distance is comparable to wavelength of light, visible light, then diffraction is significant. Or diffraction, we notice diffractions. So because of this, we have to talk about resolving powers. So therefore, this is one very, very important, right? So if this distance between the two, that the wavelength of light is goes from 700 nanometer to 400 nanometers. So if the distance between the two microscopic particles are comparable to this distance, then we talk about resolving power, then we talk about diffractions. So if distance is much greater, alright, if this distance is much greater than wavelength, then we don't need to talk about resolving power, then diffraction, we won't get diffractions, right? So this is one very important concept. So with this, I'm going to start resolving power in case of microscope. Alright. So again, same. I'm going to start. This is the now in case of microscope, what we are going to put is we are going to keep object very close to a focal length, just beyond focal length. So that means object distance is almost equal to focal length. All right. Since object distance is almost equal to focal length, object is just beyond focal length. Image is going to be enlarged. All right. Image is going to be enlarged. All right. And let's say the distance of image distance is going to be. This is object distance. And V is going to be an image distance, and diffraction pattern forms at a distance V, that is the image. Image is nothing but diffraction patterns, right? That diffraction pattern is nothing but image of an object, right? So this is what we have. So this is almost F, and now this is the diffraction patterns. Central bright. This is a diffraction pattern, central bright, V. Now this is what. Now look at here. Now when we talk about the resolving power, all right. If we could distinguish two images and then a microscopic object, then we say that it is resolved. If the two images of a microscopic particles are not distinguished, right? If we could not distinguish or not distinct or not separated, then we say that it is not resolved, unresolved. Alright, so this is what we have. And this is the size of image. Again, same concept. This is the size of image. Again, I am repeating, right? Let's say we are going to take the image. If we could able to distinguish, if we could able to separate two images of two microscopic particles, then we say that we resolved. Alright? If we could not, then we say that two microscopic particles, we could not resolve two microscopic particles. So that you should keep in mind. Very, very important, right? Now look at here. Now let's say this theta is angle. Let's say this theta is given by 1.22 lambda divided by t. This is the angular separation. This is the angle, right? This is the angle subtended by this theta, right? This theta is given by 1.22 lambda divided by d. This is theta, right? And now look at here. And then what about the magnification given by our objective lens? So magnifications by objective lens is going to be V by U, and I can write, since U is almost equal to F, I can write something like this. Now look at here, this again, this size, the beta defines the size of objective lens. This beta defines the size of objective lens. So therefore we say that 10 beta is equal to D by 2 F. So this is equal to D by F is equal to 2 10 beta. And this gives you an idea about objective lens, which is very essential for understanding resolving power, right? Now we would like to see image, size of image. What is the size of image? Size of image would be equal to, let's say, a size of image. Size of image. If a size of image is bigger, then resolving power is less, which we discussed, right? So size of image is what we define as, this is what we define as a size of image. V is image distance, and theta is angular separations. So therefore size of image is defined by V 1.22 lambda divided by F. This is the size of image. And again I'm telling you that if we put, if I say, if the images, right, two images of two microscopic particles are distinguishables, then we call it as resolving this as this is fully resolved. All right. So this is what we are going to see. Now what we would like to find is, we would like to find a limit. All right. We would like to find a limit such that the two distance at that particular two distance, two microscopic particles, distance between two microscopic particles, it is just resolved. So we would like to have a limit called a just resolve. We would like to have a limit called a just resolve. Limit. We would like to define a limit that is what we call as a just resolve. Just resolve. Just resolve. We would like to find a limit called a just resolve, and that is, look at here. So what is the size of an object? What is the size that is defined by? We would like to define a minimum distance. That is what we call as a minimum distance. And that minimum distance, so this is what I would like to define. A minimum distance. This minimum distance corresponding to this image, right? The image of this image corresponding to this minimum distance. All right. So that means if for this image, all right, two images of a microscopic particle are just resolved. This is a limit where two images of a microscopic particle are just resolved. Again, I am repeating. This is the image. This is a limit, or this is the images of this is an image of two microscopic particles which are just resolved. The corresponding distance is what we define as minimum distance. How to find how to get you this minimum distance? This minimum distance can be obtained by just divided by n. N is a magnifications. If I divide this by a magnification, we would get the actual distance between two microscopic particles, right? So this is what we have. This is the actual distance between the two microscopic particles, right? So this is what we have. This is how I define this: 1.22 lambda divided by d, and then v by m. So now this is the minimum distance, m. Now and look at here. This minimum distance is the characteristic of a microscope. All right. This is nothing to do with a microscopic particle. This is all characteristic of microscope. All right. So therefore, I would like to write this. I would like to put a value of n. What is n? N is given by v by f. N is given by v by f. V cancel out. 1.2 lambda divided by d, and then this is what we have, f. Okay, and now I would like to use this equation, right? So that is, again, I would like to say this minimum distance is going to be 1.22 lambda f by d. F by d. What is f by d? F by d is 1 by 10. This is going to be, so I use this 210 beta. Alright. So beta is very small. Normally we choose this objective length very small. So therefore, for a small beta, small beta, 10 beta is almost equal to sine beta. So therefore, this minimum distance is going to be 1.22 lambda divided by 2 sine beta. Okay, so this is the characteristic of objective length. Alright, this is the wavelength. Now, what I told you is, if a minimum distance is what we call as a characteristic of microscope. So, if a minimum distance is smaller, then microscope will have a better resolving power. And if a minimum distance is bigger, alright, then resolving power is going to be less. So, therefore, the characteristic of a microscope is all determined by minimum distance. So, therefore, resolving power of microscope can be defined as reciprocal of minimum distance, reciprocal of a minimum distance, reciprocal of a minimum distance, and that is given by 2 sine beta divided by 1.22 lambda. This is what we have. This is the resolving power. This is the resolving power of microscope. And now, one more information I would like to give you is, what about if I use, if I put this in a medium, another medium of refractive index n. So that is again we have, why? Because then that glass to this bending is going to change. So therefore we have effect of what I call as effect of mediums, right? This is what I call as effect of mediums. Effect of mediums. So if I use medium, right? Medium, that is, if I put a microscopic particle in a medium of refractive index n, then minimum distance is going to change. So minimum distance is going to be 1.22 lambda divided by 2n sine beta. This is what we have. So again, so if I use mediums of greater optical density, then optical resolving power is going to become greater, and then resolving power is going to be 2n sine beta divided by 1.22 lambda. So this is resolving power when we use a medium. Then again, now we come across one very important microscope you might heard about. So the resolving power of microscope is defined by this refractive index. This is refractive index, and then this is 2, and this is defined by objective lens. Again, this is what we define as a wavelength. So if we use wavelength, this is one very important, right? So when we use optical microscopes, wavelength almost remains same. So therefore, this is the limitation of an optical microscope, that we cannot go beyond certain distance. All right. Let's say if I say if a distance between our two microscopic particle is, let's say, 700 nanometers, then we cannot use optical microscope. Why? Because diffraction will affect. Alright, so what we are going to use then? Alright, so therefore you might have heard about something called electron microscopes. Why these days people prefer electron microscope to see much smaller objects? The reason is here. Again, this is, since it is important, I write here. Look at here. When I use the electron microscopes, I am sending electrons. When I use an electron microscope, I am sending electrons. And electron will have a wave natures. The wavelength of electron is of few angstroms, right? That is 10 is for minus 10, something like that. So the wavelength of an electron is much smaller than the wavelength of visible light. Therefore, electron could see much smaller particles. Electron could distinguish much smaller particles. Alright, so this is the benefit, this is the advantage of electron microscope. The reason is that since electron having much smaller wavelength and electron could see much smaller particles. Alright, electron could see particles, alright, much smaller particles, right? So therefore electron microscope, this is the reason why we use electron microscope. Alright, so I've done with this. In this case we have an electron microscope. In case of a telescope, we talk about X-ray telescopes, again determined by a wavelength. This is again determined by a wavelength. Okay, with this we have done with resolving powers for microscope as well as telescope. Thank you.